The pressure felt by an object immersed in a fluid, that is, a gas or a liquid, is proportional to the depth at which the object is located. Pressure of this kind is related to the weight of gas or liquid which lies above the object. Here we see two objects immersed in water. Now the mass of a given volume of a substance is equal to the volume of the substance multiplied by its density, and the weight of any substance is its mass times the acceleration due to gravity, represented by g. So in order to work out the weight pressing on each of the objects you see on screen, we need first of all to find out the volume and the density of the column of water which lies above them. The volume of the column of water is the horizontal area of the object times the height of the water lying above the object. Having calculated the volume of the water column, we multiply that volume by the density of water to give us the mass of the water column. We then multiply this mass by the acceleration due to gravity to get the weight of the water column. The weight of the water column is the force acting downwards on the object. So if we divide the weight of the column by the horizontal area of the object, we obtain the pressure exerted by the water column on that object. Note that we can write weight as either mass times gravitational acceleration, that is m times g, or as volume of the water column times density of water times g, that's v rho g. But as volume v equals area A times height h, the weight of the water column can also be written as A times h times rho times g. To calculate pressure at depth within a fluid, we choose this latter way of setting out the equation for pressure. We obtain then pressure at depth equals weight of fluid divided by the area of the object, which is A times h times rho times g divided by A. By cancelling out the area A, we arrive at the standard equation for pressure at depth in a fluid. Pressure equals h rho g. That means h times rho times g. The Greek letter rho, which looks like an English letter P, is the symbol commonly used to represent density. From this equation, we can see that because the acceleration due to gravity can be considered a constant, the pressure exerted on an object immersed in a gas or liquid is proportional only to the height of the gas or liquid above the object and the density of the gas or liquid. The pressure calculated using the equation on screen is often referred to as the hydrostatic pressure and is commonly used to calculate pressures underwater at various depths. Let's now look at an actual example which will confirm that the pressure in a fluid is related to depth. This drinks bottle is filled with water, and 3 small holes are made in the side at various heights. When the top is removed, water flows out of the bottle from the holes in the side of the bottle in the manner you see here. This demonstration proves that the water pressure in the bottle at the 3 holes is proportional to the depth of the water. The further the holes are from the top of the surface of the water, the greater the pressure is at that particular point. The bottom hole is under the highest pressure and therefore squirts the water the greatest distance. This next experiment shows just how high atmospheric pressure is at the surface of the Earth. Take a second plastic drinks bottle and start to remove the air from it. The plastic bottle will then begin to collapse. What is it that causes this collapse? Let's look at what happens. Before any air is removed from the bottle, atmospheric pressure is acting both inside and outside the bottle. So the pressure inside the bottle is equal to the pressure outside the bottle. The two pressures balance and the bottle is as normal. But as the air is removed from the bottle, the air remaining, which of course continues to fill the bottle, becomes less and less dense because mass is being removed while volume remains the same. If you look at any of the pressure equations we have met, you will see that by lowering density, we are also lowering pressure. So there is now a difference in pressure between the inside and the outside of the bottle. The pressure inside the bottle pushing outwards is now less than the atmospheric pressure pressing inwards. It is this pressure differential across the surface of the plastic bottle which causes the bottle to begin to crumple. As the pressure in the bottle decreases, the difference in the pressures acting inside the bottle and outside the bottle becomes greater. Because the plastic material of the bottle is not particularly strong, it doesn't take long for the bottle to collapse inwards due to the difference in pressures.